You're listening to Don't Waste Water.
There's about 7 times the energy in wastewater than it takes to actually process it. So, clearly there's a surplus of energy there to be had.
Hello, bonjour, and welcome to the Don't Waste Water podcast.
I was doing quite a bit of that out of my apartment very early on. I had my concerns at times about people's reactions to the glassware in the windows and what they thought I was really doing in that lab there.
I'm your host, Antoine Walter, and in today's episode, I'm delighted to welcome Carol Maxwell and Brent Solina as my guests.
Biology doesn't use Twitter. Ours can. Right now, we're focused on interpreting the data and collecting it. But as we start to round out the software, we can absolutely have it so that the bugs not only let you know, hey, I need some help here, but they can contact your operator and set up a calendar invite for you that shows up right on your Google Calendar with no intervention.
Carol and Brent are respectively CEO and CTO of Microorganic Technologies.
That's the benefit from what we do. It's not what we're trying to do is to decarbonize, but it does have that massive ability to do that.
Microorganic builds a microbial fuel cell platform that aims to change the way the world deals with wastewater. Wastewater is a fascinating substance. If you're a regular listener of that podcast, you've heard me telling how it theoretically contains about 7 times the energy needed to treat it. Now, the way we deal with it today is the total opposite. We're spending a huge amount of energy to destroy that chemical potential of sewage. How huge, you ask? Well, as Brent will share in a minute, we're talking of about 4% of the US's energy use that's employed in the blowers that turn biological basins into the brown jacuzzis we all know. Does it work? Yes. Is it energetically optimized? Of course not. But if we're honest, it's still the best way to deal with wastewater that we have at hand today. The good news is that this could soon be history. Brilliant minds and entrepreneurs are at work to correct the incongruity of spending carbon-intensive energy to destroy energy. Microbial fuel cells, for instance, could decrease the energy needs of wastewater treatment plants by 85 to 90%, and that's maybe still not the most promising of their features. Yes, they produce a clean DC electrical output. Yes, they're modular and adapted to basically any kind of wastewater, but even better, they could drastically ease up the operation of plants. I won't spoil you the full explanation because Carol and Brent will do that much better than me in a minute, but let me tease you with that. Whenever your bacteria are upset because of sudden condition changes or a piece of dysfunctional equipment, they can put a reminder on your calendar. Think of that. No forensics anymore to understand what could be wrong with that complex treatment system, or even worse, what was punctually wrong and disappeared now that you're physically back on the plant. Bacteria can talk. How cool is that? By now, you're probably as hyped as me, so I'll stop talking and let you dive into the fascinating world of microbial fuel cells with Carol and Brent. Right before, let me remind you that if you like what you hear, you can help me out tremendously by sharing that content around you. Please tell your friends, colleagues, or LinkedIn network what you learned and found inspiring in what Brent and Carol shared today. And if you don't like what you hear, please reach out to me and tell me what I should be doing differently or better. Come on, do it, and I'll meet you on the other side.
You're listening to Don't Waste Water, the podcast that helps water professionals to improve their wastewater treatment, optimize their operation costs, and keep up with the latest market trends. This podcast is brought to you by GF Piping Systems. As a leading supplier of piping systems made of plastics and metal, GF Piping Systems is the global expert for the safe and reliable transportation of water, chemicals, and gas. For more information, visit gfps.com.
Hi, Carol. Hi, Brent. Welcome to the show.
Thank you for having us.
Actually, you're 2 on 1, so be kind with me. I'm alone. Jokes aside, we will be exploring today a topic which we scratched a little bit on that microphone in the past, but which is really amazing. It's one of my recurring themes to say that wastewater is actually liquid energy. And you're actually walking that talk and you're turning wastewater into energy. But we'll go to the nitty-gritties of that and try to understand a bit more what you're doing. Yet, we have traditions on that microphone, and that starts with a postcard. And you're sending me a postcard today from Albany. So what can you tell me about Albany, which I will ignore by now?
I'd say Albany, again, easy to point out. We're about 3 hours north of New York City. So we are in New York, but as I mentioned, part of this interview, we had horses going past my front door here. So certainly not Manhattan. It's a wonderful area to work. We are an hour south of the Adirondacks, an hour north of the Catskills, and an hour west of the Berkshires. I will say there's a lot of industrial manufacturing resources around here. One of our biggest challenges has been Albany has quite a bit of fresh water and cheap power, and that has made our lives difficult at some points, despite what a blessing that is.
Brent, you're the CTO of Microorganic. Carol, you're the CEO of Microorganic. Is it a good start and a good opening question to ask one of you to give me the elevator pitch to Microorganic?
Sure.
Yeah.
I think that's more your domain, Carol.
Okay. All right. Well, Microorganic Technologies is a young company that's developing microbial fuel cells for very high energy efficiency wastewater treatment. And basically, the technology reduces energy use in secondary treatment by about 85 to 90%. It also generates clean DC power, and it creates real-time process intelligence on what's happening in the system continuously. And as far as we know, there's no other technology that can provide those benefits.
Carol, actually, to get to know you a bit better, you're a bit of an outlier in the list of entrepreneurs I had on that microphone, because usually you see technical people or you see people coming from a different industry, which are then bringing something which works somewhere else and bring it inside that industry. And you are from a sales and marketing background, which is a bit less common, let's say.
Yes.
What does that bring to the table?
Well, first of all, I have done other things than marketing and sales in college. I was a biology major with also a lot of chemistry and physics. And I started out after college in a PhD program. And then I realized I didn't want to be in academia. And so I bailed. But because of my biology background, I ended up my first real job was with Eli Lilly and Company, the pharmaceuticals company. And at that kind of company, unless you're a lawyer or a scientist, a bench scientist, that company makes you what they call carry a bag. In other words, you have to meet customers and get sales. And that was something that I was a little miffed about when that happened. But actually, it was a great entree into learning about how do you sell? How do you do a bad job at selling? And so I went from, okay, I'll take this job to actually loving it. And it gave me a lot of exposure that I wouldn't have had. So I'd say that sales and marketing is a pretty big part of any company. If you don't have sales and marketing, you're not going to make very much money. So that's where I bring a lot to the table.
On the other end, Brent, you're, if I'm right, straight out of technical and research background into microorganic. What's the story there?
Yes, started as a undergraduate at Rensselaer Polytechnic Institute here in Troy, New York. My original focus and my academic focus was actually in protein folding. So how enzymes get their shape and function. As part of my undergraduate experience, I started working with a company by the name of Ecovative Design that is doing a biopolymer production from mushrooms. And when we started, they were very early stage. That's kind of how I got the itch for the startup world, because to be quite frank, I could see them meeting problems head on and stumbling through the growth process. And that's when it hit for me that anybody can do this kind of thing if you're creative enough and push hard enough at it. I had originally started doing the kind of student business plan competition circuits around on-site composting for reduction of food waste. And of course, in food waste, it's equally important as it is in wastewater that you have energy efficient aeration, which is how I had stumbled onto this absolutely amazing technology that we'll be talking about today.
When you say stumble upon, how do you stumble upon the technology?
Well, so again, in food waste and in composting, there's a lot of energy, just like in wastewater, that is spent providing the air to avoid an anaerobic condition and get proper breakdown. I always like to say that at the end of the day, wastewater treatment is really just liquid composting. It is, of course, just a lot more difficult to get oxygen into water than it is into a pile of compost. So in exploring that, I read about microbial fuel cell, which, as we'll talk about, just sidestepped the problem altogether. I was able to see that and look at the microbial fuel cell's ability to essentially provide aeration through a wire and avoid all of the blowers, everything that was associated with that. And that really drove home to me what a new piece of technology this was, and just a complete paradigm shift within the wastewater treatment space.
To finish and round off that introduction, how do you get to work together, Carol and Brent? What's the encounter, and how do you feel that's the right way to develop that thing together?
It was kind of capricious that we met. I still belong to an angel group in the Albany area. I think we started in 2008 or 2010, something like that. And one day, one of the guys that was the founder of it, he brought in Brent, and maybe it was our first meeting, I think. And he just said, I want to introduce you guys to Brent here, because he's been working on this. And I think you were maybe still at RPI at that time. I'm not sure, Brent, but
right towards the end. Yeah.
Yeah. And the guy basically said, okay, we're not ready to invest in him now, but we should keep an eye on him because this is really exciting. And most of the people in my angel group are lawyers or things like that. They don't have a lot of technical knowledge, but as a biologist, I was like, I want to hear more about that. And so we started talking, and then eventually it got to spending more time with him, and we expanded a board, and then somehow I became CEO.
I'd like to expand on that a little bit if I can. I started just by starting. Another thing that really attracted me to this technology is, at the end of the day, it being wastewater means it's a mixed culture. So you have no need for a sterile clean room environment. The materials are inherently low cost because they have to be scalable, right? And that really lends itself quite well to just early experimentation and figuring out what the technology development plan is. So that all immediately made sense to Carol. She saw the same thing I did, which is saying, at the end of the day, all chemistry, including biochemistry, is electrons moving around. And this is a natural way to kind of tap into this whole notion that life is electric, and a real big way to address, a problem here where the bottleneck for the technology appeared at that point, and in large part still is, large-scale manufacture of some of these components.
You should make a really short story about the cog.
We are kind of glossing over a whole part of our history here where, like I said, we started just by starting. So before Carol was really involved, I was doing quite a bit of that out of my apartment very early on. I had my concerns at times about people's reactions to the glassware in the windows and what they thought I was really doing in that lab there. And at a certain point, I realized that just wouldn't work. And Albany and Troy in particular hosts quite a lot of creative startups. And it turned out I wasn't the only one who was trying to use my apartment for things it probably shouldn't have been used for. And we were able to put together the Troy Center of Gravity, which was a makerspace back when that was still a relatively new concept. I remember having to explain it to people as a heavy metal gym, that you pay a membership and you get to use the machines. Now people understand the concept, but at that point, it was still pretty new. And I'm happy to say that, has since expanded. They have a beautiful new facility. They continue teaching classes to this day, and it's a wonderful asset for the community. Similarly, early on, we were engaged in a great program with, of all things, a local school district. They had a population decline, but, we're looking to get utility out of a building that was mostly empty classrooms. And so they started offering that space to startups in exchange for us participating with their academic curriculum. So it was a wonderful way to teach some of these students, and if we have our way, some of our future employees one day maybe, about this brand new technology that, frankly, some of the folks at the PhD level were still kind of struggling to wrap their heads around. So it's certainly an interesting origin, I like to think.
Talking of this technology, I have a stupid and simple question to open the deep dive, which is, your very first accelerator, the very first startup accelerator you went through was an energy one. And you said life is electric after all. So are you in the energy sector or are you in the water sector?
We're in both. It's impossible for us to pick which child is the right child.
And on the subject of energy for microbial fuel cells, the stat that gets kind of bandied around a lot is that there's about 7 times the energy in wastewater than it takes to actually process it. So, clearly there's a surplus of energy there to be had. Again, what was very attractive to us about the technology is there's a very natural progression to the life cycle. We have an immediate value opportunity in the ability to turn off the aerators. And while we're laying the technological foundation for power generation at a future date. Again, it's part of what led to our overall process and our focus on development is that there's a very rich and active academic community exploring every nook and cranny of what this technology can do. And we've sort of taken the mantle of manufacturing full-scale systems to act as a platform for everything that community is working on as we move forward.
If I get that right, that means that there's a lot of academic research about MFCs, so microbial fuel cells. What was missing? So this part of the chain which was missing was how to execute on it, how to make it, how to turn it real,
That's
how to
right.
industrialize it. And that's the challenge you wanted to solve.
Absolutely.
Am I oversimplifying it?
No, I mean, it's actually surprisingly simple, but in retrospect, again, it's a incredibly interdisciplinary technology and a total paradigm shift for the wastewater space. So what you saw is that despite all of this wonderful bench scale data and everything the academic community was leaning hard into solving, there was still this handoff that was missing between academia and industry. To put it simply, there just weren't the components to build larger reactors. Everything was handmade. There are a couple of researchers that I know very painstakingly went through fabricating some of those components just by hand so that they could do larger studies. But of course, industry wants to see larger scale pilots, and you're not going to get the funding to start researching manufacturing techniques of these critical components until that pilot's there. But to do that pilot, you of course need the large scale components. So that was this very chicken and egg problem that we just kind of dove head on into and said, okay, nothing is going to get solved here until we figure out how to scale specifically the cathodes.
Well, that is true. But there is also, Brent is being a little optimistic about that because in a way, I mean, there were lots of researchers that were trying to create materials, but as far as we know, there hasn't been any real academic success regarding the materials themselves. And so a lot of what we were doing very early on in the company was figuring out what is really the right materials that we need to make the cathodes themselves, because that's really where it all has to happen. We had to have a plan to have it be workable in industrial situations, not at lab. And that took us quite a bit of time to really keep perfecting that. And I think we're still kind of perfecting our materials now even.
I'd like to understand that material element. First, for the people listening to that, I know it's sometimes difficult when we discuss technical topics to figure out what we're exactly discussing. So I'm linking in the show notes the very good webpage of Microorganic, which is explaining how all of that works. I mean, I've seen websites describing that process. I've never seen one which was so much straight to the point and easy to digest. So if there's one you need to read about that, it's that one, and it will take you 2 minutes and you will get it. Basically, in a microbial fuel cell, you have a anode and you have a cathode. And if I get you right, the trick so far to scale things up was the cathode side. What did you find out and what are you doing differently, which somehow solves it?
First, yes, you've got that exactly correct. And for those of us that are listening right now and unable to click on the website, at a very top level, a microbial fuel cell features, as you just said, an anode and cathode with a community of microorganisms on the anode who are using that as part of their respiratory process. They push the electrons into the anode. Those electrons flow through an external circuit onto the cathode, which then transfers that electron to atmospheric oxygen in the air. So from their perspective, it's just like they're breathing using oxygen. The only difference is that their electron transport chain is literally a electron transport wire. So that's where I often describe it as a electrochemical snorkel. It allows the microorganisms to respirate using oxygen, do aerobic metabolic respiration without ever coming into contact with the oxygen, which of course means no blowers. So to your question on the challenges around the cathode, a huge component of it was just simply physical scale. When you're looking at equipment that needs to be in aeration basins that can be acres and acres large, and forgive me, that's not metric, but you need physically large cathodes to be able to do that. You can't be looking at installing hundreds of thousands of these small electrodes and then maintaining all of them. I think it's also important to remember the context in which all this was happening. Right now, we're used to fast charging cell phones, and batteries have grown just at light speed over the last 10 years. But when we were starting, electrochemistry was still largely a dark art. You certainly didn't know, even in technical fields, unless you were in electrochemistry, terms like activation losses, mass transport losses, that was not something that people were familiar with. And again, what we were discussing with Carol, we're going to people that are in wastewater, pretty far removed from electrochemistry, talking about the challenges we're addressing at our cathode and using these electrochemical terms that were just not on anybody's radar at that point in time. So the challenges with the cathode, one was the physical scale. Two is that while we are a living battery, the electrolyte we use is sewage. So we don't get the same kind of trick playbook that battery researchers and manufacturers do, where we can use things like phosphoric acid and where they just have this really tight control of the chemical environment. Certainly anybody in wastewater will say it's anything but consistent. So, that really curtailed the number of catalysts that we could be looking at. It curtailed the kind of materials we were looking at. It really shaped the kind of geometry we were looking at, which in turn also drives the physical manufacturing process. We've tried a number of different large-scale manufacturing platforms before settling on where we are now, and that was the biggest challenge.
So going to the end of the story, so I'm really now fast-forwarding to the result. Mm-hmm. That ends up being Viva, which is your product today. The reason why I'm fast-forwarding is just to understand that step. You said that you don't want to have thousands of small size MFCs, which you would have to fit into your treatment. How much wastewater can you treat at once with one Viva unit to get a sense of scale?
Yeah. So the scale that we're at right now, we're doing about 400 gallons a day at Anheuser-Busch. What's important about that pilot is the retention time that we have it set to right now is about half of their current process. To give you an overall sense of the scale of the unit, it's if you could picture something roughly the size of a refrigerator that features both the anodes and cathodes in a cassette, similar to how you might look at a membrane filtration module, that is sitting in the tank at Anheuser-Busch. So that module could likely support a much larger tank and as a result, a much larger footprint, but that is the kind of size constraint that we went with for this pilot.
Okay, so that answers my question on the size, and that gives me a hint with your retention time divided by 2 towards the advantages of your solution against the status quo. And you gave us in the elevator pitch already some hints, Carol, but now really circling back to the challenge we have to solve in the wastewater industry. Out of all of those challenges, if you had to pick only, I'd say 3, which are the 3 top challenges which you can solve with MFCs?
First and foremost is turning off those blowers. That is, depending on which stat you go by here in the US, that's somewhere between 3 and 5% of US energy use goes to running those blowers. And again, I think that stat is a bit inflated, but it's clearly a very large problem. And there's knock-on effects to that. Those blowers require quite a bit of maintenance, quite a bit of service as they go. They drive not only the energy requirements of the plant, but the power requirements. So you won't see even a small wastewater treatment facility that doesn't have a significant power station supporting. When they turn those blowers on and off, they typically have to let the power company know because of the effects it has on the grid. So over and above the actual energy use, there are huge implications of the power that's required at those facilities. I'd say the second, and it's one that we address quite handily by monitoring that electron flow, is just process intelligence. Wastewater, you're typically looking at daily lab workups. Biology typically isn't nice enough to tell you how it's doing. In this Internet of Things age, we're so used to being able to check whether or not the oven's on from a continent away. But, microorganisms don't typically use Twitter. So we're able to monitor that electron flow that, again, is coming directly from the respiration of the microorganisms. And that gives us a real-time indicator of how healthy our bioprocess is.
It's also, though, important to mention that that is a key component of it. But in addition to that, the potential in both the cathodes and the anodes gives you additional information that normally you wouldn't have. And for example, if the potential starts to go down, exactly where it's going down, like by the part, by the actual piece of equipment itself. Now, we haven't really experienced that, but at some point we will. And you would know if there was a part that wasn't working properly, and you'd be able to identify it specifically.
Well, we haven't really experienced the part failure. I can tell you just this morning at, Anheuser-Busch, we had an issue with one of our recirculation pumps. Just one of the breakers flipped in the building. And I was able to tell that half a state away right there on our dashboard. More importantly, I knew it wasn't a biological problem. So again, if you look at our implementation strategy where you have these cassettes that are all just dropped to an aeration basin, like Carol said, you would be able to look at that readout, know which module and which electrode needed to be pulled, brought ashore, maybe examined. And there's two important things about that. One is, as Carol said, you know exactly where the issue is. And two, while you're fixing that one module, all the rest of them are still working. You don't need to drain the tank. You're not looking at a major process disruption. It very much streamlines maintenance.
So you had number 1, turning off the blowers. Number 2, process intelligence. What is your number 3?
If I'm dragging myself outside of microbial fuel cells for a second, I would say actually the third biggest problem within specifically wastewater treatment right now is one of policy and optics around water reuse. You see a growing push for what I've seen sometimes called the pure water movement, toilet to tap, or at minimum aquifer recharge. It is outrageous to me that we spend all of this time, energy, and money and just generations of solid engineering making sure the water that leaves a treatment facility is as clean as it can be, and then we don't use it. That should be a more closed loop process, and we should be more conscientious of where the water that's leaving.
But you're cheating here because you dragged yourself out of MFC. I want to have challenges that you solve with MFC.
Gotcha.
So I want a third one that you
Absolutely.
solve with MFC.
In that case, then, if you're sending me back down into
I know where you're going now.
I won't even call it a challenge. What I would say is the most exciting opportunity about microbial fuel cells is that electron flow and separation also allows us to do energy positive desalination. That is not something that we're actively pursuing right now. We are very excited about some upcoming opportunities with Xylem and our ongoing pilot with Anheuser-Busch. But again, the ability to desalinate water and do so while generating electricity and processing waste is just, that's the holy grail of a value proposition as far as I'm concerned.
I've seen a presentation about that last week, so let's call it serendipity. And I was surprised because that presentation sounded to me like really the kind of things which is an awesome application of the 7-to-1 ratio you mentioned a bit earlier. This energy positive potential of wastewater. And what surprised me in that presentation is that the horizon they were giving for the rollout of the technology was something like in a decade or two. And it was like, okay, but we need it today. And I don't see what prevents us technically from doing it today. I'm not saying it's easy, not my point. I'm just saying that, if we want to align the stars, it sounds like something that we shall be pursuing right now. But I don't want to sidetrack you here. It was just my gut reaction.
No, and without getting too deep into microbial desalination, but that does tie into my previous point where with everything this technology does, it was so critical to develop a platform. And that's a story we're looking forward to eventually being a part of, is that with our ability to make these electrodes at a large scale, that gives folks that are doing the research right now a target to hit. With our modules, it goes from a, kind of concept of, a microbial desalination cell can do X, Y, and Z. Well, now they can picture our modules, and we have a platform that we would love to try that kind of stuff with in the future.
Let me dive a bit deeper into your first advantage, which you say is turning off the blowers. So that is the 85 to 90% energy reduction, which you hinted to, Carol, at the opening of the discussion, right?
Correct.
So that's the potential. Now there's something in what you do is that you have this aeration without air, trademark. two-side your website. I love how you trade market that one. So
Yeah,
you're still aerating a little bit, and if I'm right, that is for denitrifying.
it does help with the simultaneous nitrification and denitrification, but the small bit of air we do use is our cathode. Because it uses atmospheric air, the cathode has to have air on one side and water on the other. So the question becomes, if you want to drop in solution, how do you keep essentially a wall of air on one side of that electrode? And the answer that we came up with was we essentially have a window frame that has a cathode on both sides, and that creates a sealed pocket of air that we occasionally sort of refresh the air content of. So while we don't completely eliminate the aeration, you are moving air through air. It's at a much lower pressure, and you avoid any of the issues around oxygen transfer efficiency because, again, you're not putting that air into the water.
But doesn't that turn your cathode into a membrane aerated biofilm reactor?
So it's interesting you bring that up. A lot of the MABR companies, if you look far enough back, did originally have some microbial fuel cell DNA in them.
I can quote you, Gilad Yogev, on that microphone on that. He said, MABR is what we did while we were busy doing MFC.
Yep, that sounds about right. And I've met some of the folks at Oxymem and some of the others, and they have some really interesting stuff going on. And early on, this may have been before Carol even stepped in, we had looked at that. Just like in MABR, it's critically important that we do that gas air to liquid transfer. What is an added layer of complexity, and perhaps they were a bit smarter for going after the lower hanging fruit first, is adding that electrochemical aspect. Taking that gas transfer membrane and then getting a electrocatalytic surface attached to it and figuring out how to manufacture, that was hugely challenging. So again, if you go far enough back for a lot of the MABRs, it's a very tempting path to go to say, hey, we got the oxygen transfer going, let's maybe not do the electrocatalytic part right now. But we wanted the brass ring.
Very clear. I think we have now a good overview of the technical side of it. And I'd like to go a bit deeper in a minute on the process intelligence, but I'll keep that in the fridge for now. Mm-hmm. What I'd like to understand is something which surprised me, is that you say that your solution works for high and low strength. Most of the time, we see this kind of processes tried out in high-strength wastewater. What makes you confident in the fact that this can roll out in low-strength wastewater? Mm-hmm. And what's your different take at that matter to be so strongly differentiated there?
I can say we're confident in low-strength waste. That's an easy one to answer.
Well, we've done it. Yeah.
There's that same mind again. Again, being up here in the Northeast United States, a lot of these plants and infrastructure tend to be combined as well as fairly aged at this point. So we had a really great host in the form of the Pittsfield Municipal Wastewater Treatment Plant. It was an excellent pilot. We did that for just shy of 2 years, but they had pretty low strength waste due to primarily a lot of the infiltration that happens within their sewer system. So I will say that isn't something that we shot for, but it was nice to get that data. And at the end of the day, our approach to sizing, I think, is still relatively different to what a lot of other folks do. Our Viva module, in addition to the treatment it's providing directly, really helps to stabilize the effluent around it. So we kind of have this combination of fixed film and free-floating treatment going on, which for lower strength waste brings it pretty similar to what you'd see for either a anoxic or return activated sludge process.
So it can strive in many environments, and there's many playgrounds for Viva. Yes. Yet, let's read now a business model and sales question. What is the ideal configuration where you say, okay, if that happens, then Viva is the obvious better solution than whatever is existing out there?
I think at this point, the advantage of the technology, the larger the plant, the more they're going to care about the energy savings. Certainly at smaller plants, there are enormous benefits, but saving $10,000 at a very small plant is not going to be as interesting when something's on par with, like, let's say, resurfacing the blacktop that they have.
So it's really a matter of size. So this is a factory size.
Yes, and I'd say as we get into smaller facilities and especially food and beverage on site, the smaller facilities do get excited about the energy savings, but the process intelligence just becomes absolutely paramount. If you look at a brewery that will typically have a small package plant on site, they probably don't have a full-time person dedicated to just maintaining that equipment, because typically those package plants will operate without intervention really well until all of a sudden they don't. So while they're interested in our energy savings, and especially around brewing, we see just a very strong appeal of just good water stewardship. Having that data intelligence lets them focus more on their other operations without worrying that they're about to be in violation of their permit.
And to kind of go along with that, when you're in that kind of situation where there is something that is going a little bit south, it's not looking right, in general, a plant wouldn't really necessarily even have the scope of data that they would get from Viva to really understand, like, where is this coming from? Is it a biological problem or a mechanical problem? There's a lot of kind of getting down to the nitty gritty that you can't if you only really have in your hand just taking some chemical tests.
And similarly, that chemical sampling for food and beverage facility, that may not even be happening once a week. Yeah. Maybe it's every other week. And I said at the kind of the top of the interview that biology doesn't use Twitter. Ours can. Right now, we're focused on interpreting the data and collecting it. But as we start to round out the software, we can absolutely have it so that the bugs not only let you know, hey, I need some help here, but they can contact your operator and set up a calendar invite for you that shows up right on your Google Calendar with no intervention.
How far did you go with this Internet of Wastewater?
Oh, I like that. Can we steal that?
We better trademark it right away.
I would say right now we are still collecting a lot of the data. We make extensive use of what we've started calling a red, yellow, green kind of traffic light system. As we expand our piloting efforts with Anheuser-Busch and Xylem, we are looking at potentially employing some more big data approaches. There's just a ton of information there. And while I said previously that we didn't get to borrow a lot of the tricks that people are doing in traditional electrochemistry like batteries, a lot of that signal interpretation is immediately applicable. And there's a huge body of academic research that's growing in terms of being able to identify specific compounds, what compounds are going to be made if you poise the electrodes at specific potentials. So similar to our scale-up strategy, we are very happy right now to just get a glimpse into that world, but there's a whole treasure trove of data to be had there.
So if I try to unpack, that means that you're going right now through test and learn at your pilot or beachheads plant at Anheuser-Busch. And right now, your wastewater can already set things in your calendar, which is already crazy when you think of it. And down the line, there could be much more about it.
Yes. Yeah, absolutely. If you look at the growing field of bioelectrochemical biosensors, essentially every one of our electrodes is that. So again, we focused on getting this workhorse of treatment done, but we benefit from that body of knowledge. And clearly there's already the market pull that people really like what that field has to offer.
You mentioned Anheuser-Busch, which is very clear to me. It's the one producing the wastewater, running the plant, and probably the site where all that is hosted. You also mentioned Xylem. What does Xylem do in that equation?
So we are part of the Xylem Innovation Lab, which is a combination accelerator and incubator. And we've been working with them to identify a future pilot. And our hope would be, again, that our Viva module can be spec'd into their product offerings at a future date.
By the time this interview will be out, my interview with Sivan Zamir will be out as well. So you see, I didn't know at all that those two stories were connected, but it's interesting how those dots are always connected.
Yeah.
So it's also a good example of how it takes a village to solve the issue.
Oh, absolutely.
Yeah. And I would say that, and she's probably going to talk about it as well, they've created this kind of lab with companies that they think are very of great interest to them. And they are really looking beyond just kind of typical incubator, accelerator type of experiences. We've been getting a lot of very interesting insights and support from some of their engineering teams to help us, because we have a product that works, but it's not really fully ready for commercialization. And so being able to get some of those insights as a very small company we don't have has been extremely beneficial to us.
Yeah,
and to I think everybody else in that cohort too. They have, I think, at least 25 or 30 companies in there.
It's just been an absolutely fantastic program. And I would like to take a minute to say, if you are listening to this and you're an aspiring entrepreneur in the water space, these incubators and accelerators have gotten much better over, I'd say, even the last 5 or 6 years. And our experience with Xylem has been phenomenal, and I cannot recommend that enough.
It's interesting because that could become a series right now, because I also discussed, just the episode before this one should be the one with Scott Brent from Imagine H2, and we discussed all of that, the evolution of all the programs and everything around the startup ecosystem. But if I go into that, I'm really sidetracking you. So let me bring it back on track. Actually, my question here would be, how committed are you to push Viva and Microorganic towards the bigger scale? And it sounds like a weird question. Let me unpack it a bit. Actually, if you look at the timelines in the water industry, at the stage you're at, you would predict that your technology shall be in the middle of the market in 15 or 20 years, assuming you stick to it and you do all the right moves. First, do you believe you can speed up that curve and go against all the odds and all the historic rollout of technologies which have happened over the past 50 years, let's say? And second, if you have to endure that timeline in this conservative industry, are you ready for that?
Emphatically, yes. I think some of the timing, is always a bit subject to debate, but certainly 10 to 15 years is right out of the question. And frankly, we collectively as, the human species don't have that time. And I think there's two things coming together. You've got a increase in pressure on companies to really get their carbon footprint down, as well as just general resource constraint. And then two, without going back down that path that we talked about of looking at the whole startup ecosystem, I think the water industry is doing a much better job reaching out to earlier stage companies and more novel technologies. Everybody knows water is hard. Hardware is hard and water is really hard. But I think through these programs like the Xylem Incubator, this other accelerator, the AB InBev accelerator that we're in with Anheuser-Busch, I think you're seeing the industry start to smooth out that valley of death quite a bit and realizing that they have to play a part in getting these technologies to market.
I don't think there's a really good totally established pathway for going from where an early stage company is out, especially in the water space. But, it is kind of consistent in working now with both Xylem and Anheuser-Busch. Anheuser-Busch continuously tries to reinforce with everybody in the cohort that's there right now that they really want to deploy new technologies sooner, not later. And they're not super risk averse about this. They understand that they live with having to deal with wastewater all the time. But we weren't just like one outlier in that cohort. And the same with Xylem. They are really taking a lot of X-ray looks at what we do. It's not like some incubators where they're just trying to help you get better. They're really looking forward and to try to figure out how can we integrate this earlier rather than later. And so I think that there are ways to do that. And in fact, even potentially in the municipal space, they're not saying we can't do that.
That is all sort of at a top level. But, your question was, what are we doing to shorten that? And what are we doing to be ready to get this technology everywhere on the planet? And the answer is what it's always been, which is focus on large scale manufacturing of this critical component that just does not exist right now. When we started looking, the manufacturing process was as much of a design constraint as everything else. We prototyped on platforms that let us make these electrodes that didn't care if we were making 1 or 1 million. And I'd say right now we're in the home stretches of putting the final touches on that. But again, when we buy materials, even if we're just trialing it by 5-gram quantities, we buy it from a vendor that can get us a truckload. I have a bunch of activated carbon that frankly, we won't have a use for because I didn't like the lab results and I could only buy it in 50-pound sacks. And the same is true with, again, the equipment we use. This is all readily scalable and in a lot of ways already at scale. Whether or not we have the manpower to run it 24/7 or a willing pilot site is a different story. But we built even our prototype manufacturing with an eye towards rapid scale up.
And it is also important to remind us that in the space of water right now, with the technologies that are widely available, there are a lot of places on the planet that don't have power grids to be able to deal with even the more efficient aeration systems. They just don't have that. And so I think that's a pretty big impetus, both in terms of human safety and sanitation and ecosystems, that it's really important that has to be addressed.
I'll take the two ends of your answer. Starting with what you just said, Carol, I had a discussion on that microphone with Stefan Bissady from the Asian Development Bank.
Uh-huh.
And what the Asian Development Bank has been doing is that they've been looking at how much energy is available on the grid and how much of the wastewater still needs to be treated. And there was a problem, which was that if they were to reach a full coverage in terms of wastewater treatment, they had an energy problem. So they created a tool, which is called the screening tool for the energy evaluation of plants. And actually, the 7-to-1 figure that you reminded us at the beginning of that discussion, Brent, is part of that tool and of the note which comes with it, because they have a strong hint and incentive and at technologies which could be tapping into this chemical energy of wastewater and say, we need that, because if not, we will never strike a balance. So energy is a clear part of that equation. There's something which is surprising to me, and that's the beginning of the answer you gave me, which is you said the strongest driver might be carbon footprint. And I'm surprised that this comes 50 minutes in, because when I see what your technology does, to me, it's the obvious number one asset. I'm not saying that carbon has yet the place at the table it should have. And every time I mention carbon on that microphone or put it in a title, it's the only case in which I have haters on that podcast, which come to me and tell me that climate change is fake. But again, I'm not sidetracking here. What I want to say is that in your short resume of what Viva does, you emphasize how you're not going through the methane step.
Yeah.
And methane is awesome if you can leverage its energy, but is horrible if it gets to the atmosphere, which we do know that the brown jacuzzis have that little tendency to push methane to the atmosphere, and same with NOx emissions. So to me, I would have expected it to be like the number one. Like I ask you, what are the challenges you can solve with your technology, and say carbon. Something else? No, actually carbon. And everything is then a byproduct. How important does it become in your discussions with your partners, customers, prospects, that carbon element? Is it really something you put that on the table and say, hey, let's meet in 2030 because that's going to be a killer by then? Or is it really an argument which becomes to be effective today?
It's starting to be more effective today, even in the absence of really robust regulation around carbon emissions here in the United States. And they might be upset for me as phrasing it as being surprised, but I was very pleasantly surprised about not only the goals and the effort that both Anheuser-Busch and Xylem put into tracking the carbon footprint of their processes and equipment, but how much that becomes part of their internal report card. They really both have been talking the talk, and I'd like Carol's opinion on this, but I think the only reason we didn't really bring it up is that we've found in the past that we really need to emphasize the non-carbon aspects. So we kind of have to just scoot right by it.
It's not a critic at all.
Yeah, I mean, we have to prove that we can, that's the benefit from what we do. It's not what we're trying to do is to decarbonize, but it does have that massive ability to do that.
Mm-hmm. And I will say there's definitely been a growing focus. Similarly, I know there's a growing body of knowledge around nitrous oxide emissions that folks are becoming more concerned with. And of course, unlike methane, you can't do much useful with that, and at least not until 5 o'clock when work ends. And that has a huge carbon footprint in the atmosphere, or greenhouse gas equivalent in the atmosphere.
So I'm reassured I didn't totally misunderstand it, and carbon is a result. So it's not the number one driver, but you're looking at many things, and then as a result of all of that, you decarbonize.
Mm-hmm. And to talk about it specifically, our microorganisms love volatile fatty acids. So we curtail that methane production by, kind of essentially shunting away from that methane production, even within the bulk fluid itself.
I have a last question in this deep dive, and it's a question about your business model. Mm-hmm. Oh, let me be very blunt here. How do you intend to make money?
Selling Viva units.
Yeah, absolutely.
Again, just like our manufacturing, we had a strong focus on what ROI matters to our customers, our potential customers, and are we on our way to hit cost metrics to match? And that was a very long road because it's a very complicated pricing structure. Everybody has different pain points. as I indicated before, where we had the wind against us, is that we are right here next to the Great Lakes. We've got some of the cheapest power and cheapest water that you can find on planet Earth. That makes it hard to get traction sometimes. But if you ask how we're looking to make money, it is sales of Viva units.
So your intended business model is CapEx sales of your product. I'm just asking because from what we were discussing, it could as well be, I don't know, Internet of Wastewater as a service. And I appreciate your trademark on that, Carol. So it's trademarked on me, or leasing. Those plenty of possible business models. It's interesting.
We have not really taken a look at leasing from a financial standpoint, particularly. We are still in the process of trying to figure out what would be the cost, what would we sell Viva modules at. And that's something that we're still in this process of trying to kind of parse that out. We've been trying to talk to people about it. So far, I'd say that we have mixed feelings about this because a lot of people don't really want to open up the kimono and tell you a lot of things about it. So I think that when we're done with some of our current piloting and we have a very close view of performance of Viva that is really validated both now in municipal and in industrial, that gives us an opportunity to try to go back to engineering firms and other companies to try and get a better handle on it in terms of what is this really worth beyond, because it isn't just about the energy efficiency specifically, even though that is kind of the high point.
I'll also say when it comes to model, if you look at everything we just discussed about, we've worked very hard to have a proprietary large-scale manufacturing platform. When we're ready to light that rocket and move forward, we don't particularly want to be constrained by all of the additional engineering services that come with direct sales, supporting the installation, when there are partners out there that have those connections, have that access, and the only thing they don't have is Viva. So that doesn't lend itself quite as well to either a lease or a benefit sharing. But what it does do is leverage, again, our large-scale manufacturing capacity.
Which leads me to my closing question here. How does success look like for you on the 10-year horizon?
Say Viva in anywhere where there's biological waste that needs to be degraded, which I realize is kind of a top-level answer. But again, in leveraging our mass manufacture ability, that is what that rollout's going to look like. This is something that's applicable to low-strength waste, to high-strength waste. There's potential applications in situ environmental remediation. If you have a problem water stream, instead of diverting any of that fluid, you could put Viva modules directly in, like, let's say, a retention pond that, is having frequent algal blooms and causing issues like down in Florida, for instance. And as we grow, that's something that we don't always need to be directly involved in because people will be more familiar with the technology, be more familiar with the platform. And we will, of course, always support those use cases. There's always back and forth between the engineering firms and the equipment manufacturers, but we are really looking forward to being able to leverage all the people out there that are already trying to solve this problem and just giving them a very sharp spear to go hunting with.
I think there's also an opportunity for us working now with Xylem and with Anheuser-Busch. They're two totally different companies, but both of them are very anxious to be decarbonizing their operations. And they're also interested in innovation. And they understand that, and they've expressed this a number of times, that the reason that they're doing these incubators and accelerators isn't just to kind of learn more, but that they want to expand what they can do from a decarbonization perspective and also from their own operations. They can make them better. And so I think that in the end, the decarbonization is really important, but these companies are looking for better solutions than what they had. They want decarbonization, but it's not just about that. It is also about trying to get a better system, and that's something that we can provide. It has novel features that you really can't get anywhere else. Mm-hmm. And it gives them a lot more kind of strength in terms of evaluating how they're doing with their wastewater.
Brent, Carol, it's been a fascinating dive into microbial fuel cells and your take at it with Viva. And I think I got some nuggets, and I think I understand a bit better all of that scene, so thanks a lot for that. I propose you to round it off by switching to the rapid fire questions.
Oh, okay.
Oh boy.
It's time for the rapid fire questions.
I'll try to direct them at each of you one by one.
Okay.
So I'll start with you, Carol. And what is the most exciting project you've been working on and why?
I would say that the most exciting project that we've worked on is actually the Xylem pilot right now. We're a very small company, and so we have access to quite a few engineers in different capacities that have really upped our game quite a bit in terms of really understanding a lot more about the bigger picture of water.
Brent, can you name one thing that you've learned the hard way?
All of it? No, I would say one of the most difficult things in doing the scale up is, again, my background has been biochemistry. Having to learn how to code a PLC, control systems, design pump systems, especially Pittsfield, where it was reaching negative 20 degrees Fahrenheit when we were installing. That was absolutely trial by fire, absolutely brutal. And I'd say that's the thing that was an unintended lesson. I'll put it that way.
I've read that story on your website preparing that episode, and first I didn't understand because it wasn't written Fahrenheit, it was written degree, and to me that was pretty hot. So then I found out it was Fahrenheit, and that was pretty cold. But
yeah,
negative
stupid
20.
Europe and me, sorry.
No, yeah, negative 20. I can tell you I would set my watch. It was a 7-minute timer. If I had to stop flow to do any modifications in the line, I had 7 minutes before that line would freeze solid till the spring. That was brutal.
I imagine the challenge. Carol, is there something you are doing today in your job that you will not be doing in 10 years?
I won't be making pitch decks.
You would be surprised at how often that answer comes.
That's right, because it's really the least fun part of my day. And I'm not very good at it, I think, overall. So.
Oh, she's too modest.
I don't know about that.
Brent, what is the trend to watch out for in the water sector?
Well, I have been paying a lot of attention to this microbial fuel cell space, and I think that's really going places. All jokes aside, I mean, again, I am biased, but when we're talking about something that has the potential to do energy positive desalination in the future, when we're talking about something that has impacts on home septic, environmental remediation, small plants, large plants, and as well as the data, if I didn't feel that way and couldn't answer the question saying microbial fuel cells, I would not be here.
Yeah, that is a really good point. We didn't address it before, but microbial fuel cells don't have to be only for industrial settings. And there are, even in the United States, a lot of places that they don't have sewer systems necessarily, or very good ones. And there are a lot of people that don't have good septic either. And so we have all other ways to go in terms of basically using the same technology and even somewhat the same format, but just size it down.
If you open that sidetrack, then let me follow it. Because when you think of it, the way you just explained it, there's one hot trend which usually comes as an answer to that question with a lot of my guests, which is the trend for distributed or decentralized treatment. And what you need for that is a system which is sturdy, which apparently your system is. But the number one feature is that it needs to be connected and automated, because if your system is distributed, you cannot afford to have an engineer or a technician sitting next to it 24/7. That would be stupid, and that would defeat the full scalability of the experiment. Mm-hmm. And here you have something which is beyond automated and connected, because you have your bacteria which are dragging things in your calendar, which I'm still amazed. And I'm wondering how much of that difficult and blue ocean vertical are you exploring now of this decentralized distributed treatments which everybody could have basically in their backyard?
I think it's something that is firmly on our radar. And again, especially with somebody like Xylem that has reason to be focusing on those markets, it's definitely, a conversation to be had. But I think Carol would agree. Right now, we're focusing on these pilots that are right in front of us.
Yeah. A couple years from now, that would be fun to really try and get into it, because those problems are still going to be there.
Right. And we want this Viva module perfected bomb-proof with just mountains of data behind it. And then exploring all of those other applications we talked about is going to be a much easier transition.
Which is probably the reason why you're in business and I'm asking questions, because focus is the number one thing before going in all the tangents and sidetrack that I can imagine. Carol, if you were a world political leader, what would be your first action to influence the fate of the world's water challenges?
I guess I would look at that probably from the human standpoint. And I think that everybody should be able to have access to basic, safe sanitation.
And for both of you to just round it off, would you have someone to recommend me that should definitely invite on that microphone anytime soon?
It's an individual by the name of Samir at Xylem. She just started heading up the incubator. She's phenomenal. I would also, recommend potentially some of the people at the AB InBev incubator. There's a large water focus there, but again, they can really give you insights into what those companies are doing to walk the walk around decarbonization. I'm continually astonished at, what they do over and above water, and they just so many elements of their business they're focusing on. I think that would be a really good program.
Well, thanks for the recommendation. And if people want to follow up with you after having listened to all of that, where shall I redirect them the best?
So if they want to just learn a little bit more about what we do, our website is the best. If they want to have a conversation or learn more about us, I would say that LinkedIn is probably the best way to reach us.
So as always, you'll find the links to all of that in the show notes. Well, Brent, Carol, it's been a huge pleasure to discuss with you and to explore all of that. I'm going to be looking where the future holds for you. And yeah, whenever you have a next big milestone to share, I'd be really happy to explore it with you. Thanks a lot.
Yeah, thank you for having us on. Yeah, I guess the last thought I'd like to leave you with is if there's one thing you take away, it's again that notion that life is electric here. What Viva allows us to do is tap into the electricity of life that's flowing around all the time right now. So when you look at wastewater, don't look at just the oxygen, don't look at just the bugs. You should be seeing lightning bolts flying all around that tank, with Viva being the extension cord to plug into that.
I'll do something which I never do, is I'll tell everyone what my intended title could be right now after this discussion. And I have two out of what you said, which was this Life is Electric, and the other was Are Your Microorganisms on Twitter? And I think if I combine both of them, maybe we have a fun and catchy thing.
Excellent.
And if the title is fully different, when you click on that, is that I change my mind. Remember, I'm French, so that happens.
Excellent. Thank you so much. This is a lot of fun. Thank you.
Thanks for listening to Don't Waste Water. This podcast was brought to you by GF Piping Systems. Loved this episode? Head over to Apple Podcasts to subscribe, rate, and leave a review. See you next time.